Scintillators are materials that produce light when ionizing radiation passes through them. These materials can be solids or liquids or gases. Scintillator materials absorb incident gamma radiation by one of the three mechanisms we discussed before. As the kinetic energy of the reaction electrons is deposited in the material, it raises the material's electrons to excited states. During the subsequent de-excitation, the scintillator usually emits a photon in the visible light range. The light emitted from the scintillator is guided to a photomultiplier tube where it interacts with the photocathode, releasing electrons. These electrons from the photocathode are guided with the help of an electric field toward the first dynode. The dinodes are coated with a material that emits secondary electrons, usually more than one. The secondary electrons from the first dynode move toward the second, and so on down the dynode string to the anode. More than 1 million electrons can be created for each electron starting from the photocathode. Hopefully, many light photons were created as the photoelectron moved through the scintillator so that a respectable signal arrives out of the PM tube. Many different scintillation materials are used for detectors. Some of the more common are sodium iodide, cesium iodide, BGO, which is chemist lingo for bismuth germanium oxide, zinc sulfide, which is the great-granddaddy of all scintillating materials. This was the original material that Rutherford used to do his scattering experiments, and lithium iodide, which is used as a neutron detector. The main reason that photomultiplier tubes are needed is that we need a large amplification because the primary signal out of the scintillation material is low. Unfortunately, this large amplification leads to poor energy resolution. To see the battle that we're trying to fight, let's pick typical values here. Scintillator efficiencies are on the order of 13% or less. Scintillator efficiencies are the ratio of the photon energy to kinetic energy of the electrons put into the scintillator material. Light losses are in the order of 2/3. It's a good day when we can steer 1/3 of the light to the photocathode in the multiplier tube. The quantum efficiency, which is the frequency in which the light hitting the photocathode is converted back to an electron, is on the order of 7 to 20%. These factors taken together lead to values of 230 eV or so per electron fed into the dynode strings of the photomultiplier. If we go calculate the full width half max of the signal from this ideal detector, we get 29 keV, and this is as good as it gets for cesium-137, which emits a 662 keV gamma ray. And believe me, it's generally much, much worse than this.